Have you ever wondered how your scheduling app magically avoids double booking you? Or how an AI can blaze through a Sudoku puzzle in like a fraction of a second? Well, it's not magic. It's actually a really powerful problem-solving framework. So today, we're going to pull back the curtain on the world of constraint satisfaction, the brain behind solving some of the world's most complex puzzles.
I mean, really think about it. When you're working on a logic puzzle, every single decision you make has this ripple effect. You put one number here, and suddenly another number can't go there. That's the real challenge, right? This whole web of interconnected rules. So how can we possibly navigate this without getting completely lost? That's the big question we're going to tackle.
Okay, so to tackle these kinds of puzzles without just randomly guessing, we need a system. And in the world of AI, that system is called the Constraint Satisfaction Problem, or CSP for short. Let's break it down with a classic example to see what that really means.
And what's so cool about a CSP is how simple it is at its core. It basically boils any problem down into just three key ingredients. First up, you've got your variables. These are just the things we need to make decisions about. Then you have the domain. That's the list of all the possible options for each variable. And finally, the constraints. These are the all-important rules of the game that tell us which combinations are okay and which aren't.
All right, let's make this real with a classic puzzle, graph coloring. Our variables, they're the four nodes, or circles you see on the screen. Our domain, that's our color palette, red, green, and blue. And the big rule, the crucial constraint, if two nodes are connected by a line, they absolutely cannot have the same color. Sounds simple enough, right? But as you're about to see, solving it isn't always so straightforward.
So how does an algorithm actually go about finding a solution? It's not just guessing. It uses a super methodical process called a backtracking search. Let's put ourselves in the algorithm's shoes and just walk through this, one logical step at a time.
We've got to start somewhere, so let's just pick node 1. We look at our domain, red, green, blue, and make our first move. Let's say we choose red. Okay, easy enough. 1 down, 3 to go.
And bam! Right away, the constraint part kicks in. The second we make node 1 red, the rules apply. Since it's connected to all the other nodes, none of them are allowed to be red anymore. And just like that, their list of possible colors, their domain, has shrunk. Now it's only green or blue for them.
All right, moving on. Let's go to node 2. We already know it can't be red, so from its legal options, green or blue, we'll just pick one. Let's assign it green. So far, so good, no rules broken yet.
See, every choice has consequences. By coloring node 2 green, we've just created a new restriction for its neighbor, node 4. Now think about node 4. We already knew it couldn't be red because of node 1. Now, because of node 2, it can't be green either. And look at that. Its domain just collapsed to a single option. Node 4 has to be blue.
Okay, we're almost there. Just 2 nodes left. Let's focus on node 3. Its only neighbor with a color right now is node 1, which is red. So that means its domain is still green-blue. We've got a choice. Let's just pick one and assign it blue. Seems fine, right? What could possibly go wrong?
Well, as it turns out, that last seemingly innocent choice has led us right into a trap. Our nice, straightforward, step-by-step process is about to slam into a brick wall.
And there it is, conflict. Let's look at our very last node, node 4. What color can it be? Well, let's see. Its neighbor, node 1, is red. Its neighbor, node 2, is green. And its neighbor, node 3, is now blue. So, it can't be red, it can't be green, and it can't be blue. It has literally 0 legal colors left. We are completely and totally stuck.
But this is where the algorithm gets really clever. When a person gets stuck like this, they might get frustrated, erase everything, and just start over. A smart algorithm doesn't do that. It performs what's called an intelligent backtrack. And this, right here, is the secret sauce.
Now, there is a huge difference between just going backward and being smart about it. Standard backtracking is like slowly retracing every single one of your steps. It's clunky and slow. Intelligent backtracking is different. It instantly asks, wait, what was the one choice that actually caused this problem? And it jumps directly back to fix that single mistake.
So the problem we had at node 4 was created the exact moment we chose to color node 3 blue. An intelligent backtrack realizes this, it ignores all the other steps in between and jumps right back to that one decision. It basically says, okay, that blue idea was a dead end. What was my other option back then? And its only other legal color was green. So this time, let's try that instead.
And just like that, the whole puzzle just clicks into place. With node 3 now green, let's look at node 4 again. Its neighbors are red from node 1 and green from nodes 2 and 3. That leaves one perfectly legal color available, blue. We assign it, and we're done. Every node has a color, and no connected nodes are the same. Case solved.
Now that was pretty efficient, but what if we could be even smarter right from the very beginning? This is where the pros come in. Professional-grade algorithms use something called heuristics to avoid even going down the wrong path in the first place. A heuristic is basically just a strategy, or a rule of thumb. It's not a guaranteed fix, but it's an educated guess that helps point the search in a much more promising direction. You can think of it as using experience to make smarter choices from the get-go.
For a puzzle like this, a really powerful heuristic is to deal with the most constrained variable first. In our graph, which node has the most connections? Node 1, right? It's connected to everything. By coloring it first, we immediately restrict the puzzle as much as possible, which forces any potential dead ends to show up much, much faster.
And the payoff for using a good heuristic is, well, it's enormous. For a slightly more complex puzzle, a brute force approach might have to check up to 64 different combinations. But by using that simple heuristic, color the most connected part first, we can find the solution in as little as 2 steps. 64 versus 2. That is not just an improvement, that is a complete game changer.
And the source material really says it best. Using heuristics in an intelligent way is the key to being time efficient. It's the difference between blindly stumbling around in the dark for an answer and strategically zeroing in on the solution.
But at the end of the day, this isn't just about coloring graphs. This is about real-world stuff, like logistics, scheduling airline flights, protein folding, designing computer chips, the principles of defining variables, domains, and constraints, and then searching intelligently are at the very heart of how we solve some of our absolute hardest problems, which really just leaves one big question. What's the next huge puzzle we're going to solve with this kind of smart search?